Assalamu alaikum. Welcome to our project demo of our semester final project of data structures and algorithms, which is the DSA Visualizer presented to you by Abdul Rehman Memon and Syed Abdullah Kashif. So, in this project, we will be visualizing different sorts of trees like segment trees, AVL trees, binary trees, also heaps and sorting algorithms that we have studied in this course so that people or students specifically could have a better understanding of how these things work, also their time complexity, comparisons, swaps, etc., and different kinds of traversals. So first of all, we will look towards trees. So this is a binary search tree in which we know that the left node has to be smaller and the right node has to be larger. So we will enter a few values. Let's say we enter 5 and then we add a smaller value like 4, so it goes on the left. And then we add a larger value like 7, so it goes on the right. So on and so forth. I can keep adding values into this tree, and what is constructed in front of me is a binary search tree. Here we can see the height of each node written with it in the subscript. Like 5 has height 2 because it is at a distance of 2 edges from the leaf node. Similarly, as we have inserted data into this binary search tree, we can also delete. Like if I want to delete this value 4, I can simply delete, and this will preserve the binary search tree. I can also search for different nodes, like I want to search for 7, so it will traverse and tell me the position of 7. Also, I can see the different visualizations of different kinds of traversals, like in order in which we know we have to go from left node L N R. So this is again presented here, L N R, again L N R. 1 5 6 7 30. So this is our in order traversal. If we go towards pre-order, then obviously that would be NLR. So NLR, NLR. This is our pre-order traversal. And then post-order, as we know, it is LRN. So LRN gives us the post-order of this specific binary search tree. Now, if you want to see the analysis, we can see here we have complexity analysis of this binary search tree. We have insertion, deletion, and searching, and also you can copy the C++ code to run if you. Now let's go towards the segment tree. Now I can enter any array for this. Let's say I enter this array of 2, 4, 6, 8, and 10. So this will give me on the leaf nodes 2, 4, 6, 8, and 10 segment tree. And now using this array, I can have different operations. As you can see here, A stands for addition, S stands for subtraction, and M stands for multiplication. So I can have these three kind of operations on this particular segment tree. Let's say I want to have the addition operation. So I write A and submit it. Now this 6 tells me, and the subscript 01 tells me that it gives me the sum of the zeroth and the first element of the array, which is 2 and 4 respectively. Now here I can see 12 is the sum of the 0 and the second element of the array, which was 2 and 6, which was 6 and 6. Now 18 gives me the sum of 8 and 10, and then 30 gives me the different sum of 12 and 18. So we can also have subtraction on this. You can see that 2 minus 4 gives me minus 2, minus 2 minus 6 gives me minus 8 plus 2 gives me minus 6. I can also have multiplication. So 2 times 4 is 8, times 6 is 48, times 80 is 3840. I can also update values, like if I want to update the index 0 to be 5. So it will first find the 0th index and update 5, and with respect to that, it will update every single node. So this is a segment tree. And then we have AVL trees. So in the AVL tree, we also know that AVL tree is a balanced tree. So let's say I add 5, then I add 4, then I add 80, then I add 70, then I add 2, then I add 40. So as you can see, as I entered 40 here, it was starting to get unbalanced. So after each insertion, the AVL tree is balanced again. Now if I want to add 100 and 3, then again 3 was getting imbalanced. So after each insertion, the AVL tree is balanced again. So we can see that the left node minus right node is not greater than 1 in any case, so it is balanced. Now I can also search for nodes. Let's say I want to search for 100, which is the last node. So it will tell me the position of 100. I can also have the in order, pre-order, and the post-order traversal in this. So if I want to go for in order, which will obviously be L and R. So L and R gives me the in order traversal of this tree. Then I have pre-order, which is NLR. So NLR. And then it gives me post-order, which is LRN. So LRN. So these are three kind of traversals that we have seen in the AVL tree. We can also have the analysis of these trees, insertion, deletion, and searching. You can also copy code to run in your favorite IDE. So that was all for trees. Now we will look towards our heap. So a heap, as we know, it has to be either a min heap or a max heap. So first of all, we will create a min heap. So I start adding elements into the heap: 10, 11, 12. We know that a min heap or a heap in general has to have the property that it has to be complete at each level, and it has to be complete on the left. So it follows all those rules. Now as I added 2 here, it saw that the 2 is the minimum element of this heap, so it brought 2 to the top. So a min heap has been created here. Now if I add a smaller element than 2, let's say first I add a larger element, let's say I add 15. Now I add 1, which is has to be the smallest element, right? So 1 being the smallest element comes on the top again. So this was a min heap. Now if I want to remove an element from the min heap, I have to remove the minimum element. Let's say I have to remove 1 from this min heap. So it will swap 1 with the leaf node, and then 2 comes on top, which is the new minimum element. So this was a min heap. If I want to create a max heap, let's say I want to add again 10 with this heap. I want to add 17. Now since 17 is the largest element of this heap, so now a max heap has been created. And if I want to remove this element, it will simply swap it with the leaf node, and now I have a new max heap created. And you can see the analysis with insertion, deletion, and fetch. You can also copy its code. Now moving on to our sorting algorithms. So let's say I shuffle this array. So this is a random array, right? So I can control the size of my array with this bar here, and let's say keep it not too large, and I can shuffle the speed of sorting. Let's say I want this array to be sorted at a good speed close to the maximum, so I keep it here. Now these are the different sorts that I can perform on this specific array: bubble sort, selection sort, merge sort, quick sort, insertion sort, and heap sort. So first of all, let's say we go for bubble sort. So this is a bubble sort. Now here you can see the number of comparisons and swaps are being updated. It also tells you the length of the array, and you can see the best, worst, and average case complexity of this particular sort, as well as the space complexity. And here you can see in bubble sort, it is comparing element to each element of the array, and the largest element is being shifted to the right. So you can see that this is a bubble sort, and it's taking its own time, which is big O of n square for an average case. And now we have this whole array sorted in bubble sort. Now let's increase the speed and see this particular sort for different, let's say, selection sort. If I go towards selection sort, so this is a selection sort being performed, and this whole array has been sorted. Now you can see the number of comparisons here are greater in the case of selection sort, as well as the number of swaps will obviously remain the same, and you can copy the code here as well. Now let's have this for merge sort. Now, because this array was already sorted, so the merge sort did not take much time, and number of swaps, as you can see here, are 0. But let's say I shuffle this array. Now I perform merge sort, and here you can see that the largest element again comes on the right side. So this was our merge sort. Now let's shuffle this array and perform quick sort. Now this is quick sort, and as you can see here, quick sort was implemented quite fast. You can see here that in the average case, quick sort performs the best n log n complexity. You can see the number of swaps and comparisons here. Let's shuffle this array, and let's see this feature here of toggle to 3D. So this is a different kind of array. You can see here that it has three-dimensional structure, and let's perform insertion sort. So this is an insertion sort in which we have one sorted part of array and the other unsorted part of array, and in each pass one element is added in the sorted part of array. So here you can see this is an insertion sort, and the smallest element in each pass is being shifted to the left. And now this is sorted. And let's toggle back to 2D and do the same array for heap sort. So this is a heap sort. Again, you can see the number of swaps, number of comparisons, and the best, worst, and average case complexity for this particular type of sort. And you can also copy the code. So this was a little overview of our DSA Visualizer, in which we looked at trees, heaps, and different kind of sorting algorithms, as well as their complexity analysis. We hope that you liked our project, and the students will get benefit from this for the future years to come. We thank you all for watching this video. Like, share, and subscribe. Thank you.